Thank you, Greta. And thank you so much for the invitation. And thank you all for being here. It's a nice weather right now, so I appreciate you being here rather than somewhere at the beach, which is where I prefer to be. But so initially, I thought I would give you a computer talk, but then I kind of concluded that I have so many formulas that I prepared, you're just not going to be able to follow. So I still have a lot of formulas, but I'll present them at a pace that hopefully will be understandable. And if I'm not understandable, you can just stop me and I explain more. If I don't tell you a few inequalities, you'll survive. So the way we're going to do this is, so as Greta said, I'm going to talk about correlation inequalities. In qualities. And what I figured, so the title is longer. I'm going to tell you about some young tableaux and Schur functions and stuff. But before I get into that, I figured I'll tell you a little bit about what kind of correlation inequalities exist and what they're useful for. Okay, because I think that's a little bit of unusual idea, and then I'll tell you some. So I'll tell you some background, kind of standard in correlation inequalities, and then I'll tell you some new stuff. So the background is going to be old, new stuff is new. Everyone okay with this? Yeah, somebody say yes. Yes, thank you, thank you. So I do like participation. So let me just do very general ideas. So this is how correlation inequalities look like times. So this means that those two events have a positive correlation, and if the inequality is reversed, that's a negative correlation. Okay? So that sounds obvious, but there is. I wanna write this 2 more times. Okay, and so one time I want to write it is sort of in a conditional probability form. So one can also write this in terms of, well, we're going to kind of assume that probability of B is greater than 0. So one can also write it in this form. And even though that's exactly the same, it does give you a different feeling. So when but there is one more version, and we kind of want I kind of want them all. So P of A intersected B times P of not A intersected not B greater or equal than, I'll just do it here, probability A intersected not B times probability not A intersected B. So it's an easy exercise to show that this is the same. But somehow the reason I want want both version is because this version gives you an idea of what's going on. So conditional probability is sort of very intuitive. While this version is the one that leads to generalizations, because you can basically take a ratio of 2 sides and sort of measure how far are we from equality. That allows you to measure independence in a somewhat better way, as if you were doing this here. Okay? All right. So I'll start sort of an overview. So let's say part 1. So the first example is due to Kirchhoff, and in this example, I'm gonna start speeding up, and so this is gonna be, let's say, simple connected graph, and let's say tau is a uniform spanning tree, and E prime are edges. then this is something, I'm going to be saying something that most of you already know. So probability, there is an H in a random spanning tree times probability, there is an H E prime in a spanning tree. So, well, before I write, this is bigger or smaller? I'll tell you compared to what? Probability E and N prime are in T. So greater or smaller? Greater, very good. So there is a negative correlation. That's how I would put it. Negative correlation for a spanning tree containing both edges. And that's already a little surprising. Very old from mid-19th century, but since this is the simplest example I'm going to give, you can sort of measure, you can sort of see how far does the theory go. Okay, it's not that obvious to prove. So this is the first example. I'm gonna and it is sort of useful to immediately understand what is the point. So if you take simple random walk on all. Let me write it this way, on all spanning trees of G. So simple random walk has a polytime mixing time. This is part of the reason why I wanted to give it on a blackboard to make it somewhat informal. I don't want to define what mixing time means. I don't want to state what do I mean by polynomial time in this particular case. But I do mean precise, whatever you're thinking, if you know any definition at all, it's going to work. Okay? So, so now, what do I mean by simple random walk in this case? Well, a simple random walk is actually simple in this case. You take a random edge in the graph that's in your tree. Sorry, a random edge in your tree, random edge from outside of the tree. You try to swap. If it works, great, new tree. If it doesn't, do again. Stay put and do again. Okay? That's the simplest random walk you can think of, and this is an observation of Feder and Mikhail. I think I have a date from '92 that Kirchhoff's theorem immediately gives you that. Okay, and now once you have that, you know what would you want to have. You want to have a similar example. So suppose we have some kind of matroid. I'm going to define it as a ground set is going to be X, set of bases is B. And you would want to have the same type of results. So let's say you have E and E prime sort of suggestively in my ground set X. And now what you would want to have is probabilities that E is in B times probability that E prime is in B. So in this particular case, B is a random base of the matroid. And you would want, let me put W, you would want to have a probability, probability that E and E prime in B. And that is not exactly true. So that's unfortunate. So no, I'll write it in a different way. So here is a theorem. So here is the this is due to John Ha, Schroeter, Wang from 21. And it's proved exactly the way you think it's proved. So the probability is that E, so I'm going to write it in this form, that's in B, times probability that E and E prime are both not in B, divided by probability E is in B, E prime is not in B, times probability, whatever is the remaining one, is less or equal to 2 times 1 minus 1 over d. D is the rank of a matroid. If you don't care about that, just think of strictly less than 2. That's actually, let's not care. That's already interesting and good enough. And so turns out there are examples of matroid, not very big one even, when this ratio is slightly bigger than 2. It's, the record is about 8, bigger than 1. The record is 8 over 7, and it's a major open problem. What is the smallest one? We don't know. But there are several lessons of that. There is a reason why we have this 2. This 2 will come up. And this 2 is a byproduct of the whole, let's call it the way John Ha calls it, Hodge-Riemann package. Okay? There is just no way using those tools to get here something better than 2. By constant beta. So, so now there should be a question here. I'll tell you what is the question. I'm so good as a teacher, I'll tell you what question you should be asking. You should be asking what's the analog of this corollary. Is the corollary still true? And it is true. Even though, so corollary, and that's another major beautiful results. I'll write Anari et al. Just for the sake of time, but in fairness, there are 3 more co-authors who showed the same result, but without using this negative correlation. So simple random walk on, and by the same result, simple random walk on basis of a matroid has a polytime mixing time.
When is that result from?
19. It's you know, things are faster in computer science. This was published in Fox or Stock. Do I have that? No, but it's from about 19. It's one of the early papers. Yes.
It's just corollary of what?
It's not a corollary. It's a corollary prime. This is like an analog of that corollary. Sorry. Yeah, it's not a corollary of this. No. So this is proved using, well, whatever they call their version of Lorentzian polynomials, which is a slightly weaker version of Hodge-Riemann package, which allows kind of better access to the technology and more flexible, and that's how it's done. Okay? Any other questions about this? Go ahead.
Yes, there's no other families of matroids that somehow have been explored for.
Oh, there is like a giant amount of literature on this. I'm giving this an example just to kind of motivate correlation inequalities, and in particular motivate this type of ratios, because that turns out to be the right way of looking of how do we somewhat relax the notion of independence or positive and negative relation. Thank you. Any other questions? Everyone good? All right. So let me mention that the analog of the analog of positive correlation is open for spanning forests. And that's so the analog of this result. I personally never believed that we tried to disprove that failed. Did it again. There is no learning here. I keep failing, but it's still probably false. But who knows? Okay. I do want to mention part of the background. Let me go a little faster. I'll skip some stuff and I'll mention So another example is, I'll call it Harris-Kleitman inequality. This is in 60, and this is 68. So separate papers. Let's see. So if you have, I'll do them in order. So if you have a P percolation, I'll write it this way. So X connected to Y, U connected with V. So that is greater or equal than a P percolation under P percolation X connected to Y times whatever it is, U connected to V. So this is absolutely obvious, except it requires a proof. Okay? But if you think about it, under P percolation, of course, once you, if you sort of think in conditional probability, if you condition of some two other vertices being connected, why would probability of connectivity between those two go down? That just doesn't make any sense. Still, so this is, the proof is by induction, but it's important. It's a wonderful, important results. To motivate this as a corollary, so let's call this a theorem, which it is. And as a corollary, this shows that a critical percolation, which you can define as a supreme overall P such that going from X to infinity is 0. So this critical percolation independent of X. So you see here, we're picking a point and looking whether it can go to infinity or not. But so basically, if we if you pick another point Y, conditioning that X is connected to Y doesn't hurt your case of going to infinity. And that's already remarkable. And as another corollary, he showed that PC of, so this is bond percolation, is greater or equal to 1/2. It was proved that it's 1/2 by Keston. But that already is a miracle. That you can use, let's call it just combinatorics, and prove a remarkable probabilistic result. You see what I mean? And everything is hinges. Everything is hinges on this correlation inequality. So once we're talking about that, it's sort of maybe let me try to fit it into this space. So suppose so I'm going to say that say A is a subset of 2 to the n, where n is the numbers from 1 up to n. So I'm going to say that this is increasing. Increasing if for every A and A, if A is a subset of A prime, then A prime is also in A. So that's an increasing event. If you're thinking of subgraphs, for example, Hamiltonian set of Hamiltonian graphs is an increasing family of graphs, while planar graphs are the opposite. So that would be decreasing. Hope I don't have to write it. So in particular, so the Kleitman version is basically saying, oh, do I have it? I don't know. So if let's say A and B increasing, then size of A intersected B. So there's a positive correlation. So size of A intersected B times 2 to the n is greater or equal than size of A times size of B. Okay? And so this is a little formalistic. So in particular, probability. So if you have a percolation on a complete graph, G is Hamiltonian conditioned. G is planar. Is going to be greater or equal than probability G is Hamiltonian. Okay, because being planar is closed down, so it's a decreasing event. That's why. Sorry, that's correct. That's why this has to be less. Do you see what I mean? So it's harder for a random graph. G Hamiltonian. So it's harder for a graph to be Hamiltonian if it's constrained to planar graphs than without the constraint. Okay, and that in itself. So this led to this result led to a giant amount of work, most famously FKG inequality, and Alswede, in even more general Alswede-Dike inequality, which I'm not going to even spell out all these people who are all wonderful. But the point is, those most general inequalities are extremely heavily used in both mathematical physics and probabilistic combinatorics. Go ahead.
Does this 2 to the power n optimal?
Say it again?
Does this 2 to the power n optimal?
Yes. Because you can have all of them 2 to the n. Okay. So this is the end of prequel part. Hope now that you're motivated. Can I move on? Okay. So what I'm going to do is I'm going to kind of start a new talk, or the talk that I actually wanted to give, so I need a little bit of a definition. So linear extensions. And so you've seen already posets in the morning. So suppose this is fine. Suppose this is a finite poset. Let's denote size of x to be n, and let f be a map from x to n that is bijective and order preserving. So linear extension is a bijection that's order preserving. Order preserving means that f of x is less than f of y for every x less than y in the poset. And the idea is that this notion generalizes standard Young tableaux if you've never seen posets but happen to have seen standard Young tableaux. And so I'm going to denote, let's see. I'm going to denote E of p number of linear extensions of p. Is everyone okay with this? So for example, if you have an n chain, number of linear extensions is what? 1. A very weak response. Let's try again. If you have an anti-chain, factorial. Very good. Very good. There is hope. Okay. So I'm going to start with. There are 2 blackboards here, right? So I'm going to start with. One inequality, which is which looks extremely basic, but it does actually encapsulate a lot of things where we're going. So this is a theorem of Fishburn. It's a corollary of a more general theorem from '84. Fishburn was an expert in social choice, and so suppose we still have that, and we have 2 elements, x, y, are minimal elements in the poset. Minimal elements means there's nothing smaller. So then we have the following result. Let me write it. I have probability f of x equal to 1. F of y equal to 2 divided by probability f of x equal to 1 times probability f of y equal to, well, f of y equal to 1. So that thing is between n over n minus 1. You can think of that as strictly greater than 1 and at most 2. Wait. Yeah. Did I get it wrong?
There's no 2 in the denominator? Just one. Oh, I think it's correct.
Yeah, it is correct.
That one was our result, not this one.
Say it again?
That one was our result, not this one.
Well, that makes plain. Okay, so Fishburn proved that, and we proved. So for those of you who are not, especially those online, this is Swee Chan. Let me write that, Swee Chan. And basically everything new is going to be joined with the home. Okay, so this result is old, and this result is kind of new. Go ahead.
Is that the same 2 as in the our result?
Philosophically, I can say a little more later, but kind of yes. And we cannot improve it for kind of the same reason. But tools are different. However, 2 is the same. I don't know how that works out. But it is what it is. So that's what, that is the result. And you can, so it's sort of worth saying that this stuff is using FKG. And that stuff uses combinatorial atlas technology that we sort of introduced with the home.
So if the 2 is the same, do you believe the true value is something closer to 1?
Yeah, we cannot make a dent in this. So I'll explain where this ratio comes in. It's not that complicated to understand, but this is complicated. Yeah, and it sort of comes from. Let me not say it. It is a little complicated. So let me. What I want to do is I want to. In the next 5 minutes, I'll overwhelm you with inequalities. So just sit tight. Don't ask questions. And I'll tell you when it's a good time to ask questions. And I'll answer them, honest. So let's see. So I'm just going to assume that you understood the notation, you understood the definition of linear extensions, and don't tell me if you didn't, because I'm not going to go through that again. So suppose A is a subset of X. So this is all, I should have written that. This is all joined with Swee. So A is a subset of X, then probability that 1, 2 is not in f of A. F of A is it's a collection. So F is a random linear extension, and A is a subset. So F of A is a collection of values that a linear extension takes on A. So we're saying that both 1 and 2 are among values taking on A, so somewhere there. So we're going to do that, and we're going to divide by product of probability 1 is wait. I'm just going to do a simpler version. Probability that 1 is in f of A squared. So that's already quite non-trivial. We're saying that it's actually, it hurts your case to knowing what 2 does.
Should those both be not in?
not n. Yeah, sorry. Correct. So, so I'll do more. You violated my order. So suppose A and B are well, let me, before I do that, I want to do a little more complicated one. A probability 1 and 2 are in f of A, so the setup is the same, times probability 1 and 2 are in f of A, one of them is not, divided by probability 1 is not in f of A, times, wait, not done yet. 2 is not, yeah, so probability, now I don't remember anymore. So this is in f of A, 2 is not in f of A squared. They're the same, doesn't matter which order you do it. So, and that is at most 1. Okay? So what we're saying is that there exists negative correlation of both 1 and 2 being in the same space. Okay? And that's just weird. So one more complicated inequality, and then I'll do an example, which is going to be very understandable. So this is just a lot of formulas I'm writing. So theorem from the same paper. So we have, so suppose A and B are minimal. Now you can see where this is coming from, minimal elements, so, and there has to be disjoint. So A, so now probability 1 in f of A, 2 is in f of A up. This is the upset you've heard before in the morning, times the same thing with B. Divided by probability 1 in f of A, 2 in f of B square, and the whole thing is less or equal to 1. Okay? So, so what we're saying is it's better for 1 and 2 to occupy different places than to be in the same subset. The reason why those things get to be a little complicated is sort of because there is no commutativity here. It's not like in the spanning trees you can just remove an edge, look at this edge and some other edge. They're not interchangeable. We have to introduce some kind of 1 and 2 to make it in an order. Do you see what I mean? And now you can start asking questions again. Everyone good with this? I know, overwhelming. Just bear with me. OK, so an example, or let's call it an application. So as you've seen before, well, if this is lambda, I'm going to denote by p lambda a poset obtained by ordering all the rows down and all the columns to the right. Okay, so there is a poset here, and then we're going to have e of p lambda to be number of standard Young tableaux of shape lambda. Yeah, everyone okay with this? Good. Well, so now we have so I'm going to consider a very small special case of our framework. So here is going to be an example. I'm going to take some kind of large diagram lambda, remove mu from that. I'm going to say that, well, suppose this one. So we have two boxes, x and y are corners. V and W next to the corners along the boundary. And now we're saying that, well, if you like, it's a corollary. Number of standard Young tableaux of lambda minus mu minus x minus y square is greater or equal than number of standard Young tableaux of lambda minus mu minus x minus v times number of standard Young tableaux of lambda minus mu minus y minus w. Okay. So what is the whole thing? So I'm saying that it's more likely that that 1 and 2 go into different corners, then they kind of go together next to each other like that. It's sort of somewhat more subtle, but that's what we get. Do you see what I mean? So if the way to think about it, if Young diagram is huge, all these numbers are basically the same. So you're not going to get a beta constant here. Okay? And we have a very subtle correlation. Okay? Subtle, but exactly half new. So let me tell you what's new here and what's not. Can you even imagine what can be half new? Okay, I'll tell you. But you can still imagine. So there is something I was hiding from you. This is what I think SAT is famous for this. So the picture is suggestive, but not always the same. So if both of these dominoes go vertically or horizontally, then this follows from, let me write them in full, Lam-Postnikov-Pylyavskyy. Well, no. Lam-Postnikov-Pylyavskyy. 2007 paper. Yes, 2 Y's. Yeah, I think that's correct. Okay. No otherwise. So, and I'll explain why. So this version and that version, this is a very special case you have to understand. Very special case of our result, and this would be new and would not follow from any previous technology at all. There is even this tiny special case. Even I tried, even if you make mu to be empty, in which case this looks like you can do it by elementary hook length formula. No, it's not going to work that easy. Okay? So already the only proof of this inequality requires the whole technology of combinatorial atlas. And when I say it requires the technology, our proof here, so it follows from that theorem, and our proof of that theorem is basically you have to take the previous paper on combinatorial atlas and add a few more pages. So it's not going to be a short proof at all. Okay. Can I move on?
Igor, is it true if you replace it by skew Schur functions, is there some positivity or not?
Excellent question, which I really didn't want to hear at this stage. So it's true here and not true there. But I'm not going to thank you.
So the monomial positivity is false and the Schur positivity is false? Or
Both. But, I mean, not just, this is Schur positive, and this is not even monomial positive. And it's really easy to see in the most basic example. But in truth, even if it was new, we still wouldn't know how to prove it, but it's not. So let me now tell you a slightly different direction and different paper, same authors. So I'm going to start with a real Fishburn theorem. As I said, the original Fishburn theorem, which is still hidden somewhere. So this one is a corollary of something. I apologize. I'll try to write high up. So I'm going to denote epsilon of p to be E of p over n factorial if p is x less and size of x is n. Is notation clear? So think of that as a relative number of linear extensions. And now suppose A and B lower order ideals. Then we have E of A union B. So epsilon of A union B, epsilon of A intersected B divided by epsilon of A, epsilon of B, and that's greater or equal to 1. That is the right version of Fishburn theorem. So in a particular case, when lower order ideals sort of trivially correspond to two elements x and y, because of the ratio of some binomial coefficients coming from the denominator, you get n over n minus 1. That's where this ratio comes in. OK? But that is, yeah.
Is it ever tight? The n over n minus 1.
Yes. And in fact, all of this is tight. Let me write that here. This is tight for p equal to an, and this is tight for p equal to c2 plus a n minus 2. So it's a chain plus an anti-chain. So you can, that answers your question, Lauren. So that cannot be improved in this form. We do want to improve it something, but like we want, anyway, but not in this, not this one. So somehow there has to be a dependence on A. Anyway, this, is this clear? Yeah? Now, I don't have too much time, but one can take this back, and one can sort of try to say, what does that mean in terms of number of, what does that mean in terms of the number of standard Young tableaux to sort of generalize this example. And so you get corollary, which is due to Björner in 2011. Let's call f of lambda to be number of standard Young tableaux of shape lambda divided by n factorial. So we're basically saying that f, what was that? F of, let's use another letter, f of mu union nu times f of mu intersected nu divided by f of mu times f of nu, and that is greater or equal to 1, where f is basically a relative number of standard Young tableaux. And from this point, the history sort of went a little haywire. So there is a theorem of, I'll write L and P for Lam and Pylyavskyy. So it's a different paper from LPP. So there is an analog for skew shapes So for skew shapes, I really need to tell you how to take a union intersection. Otherwise, you would know all the definitions. And to take a union, so if you have lambda minus alpha union mu minus beta, this has to be equal to lambda union mu minus alpha union beta. So that's how you define a union intersection of Young diagrams, where here the union intersection is sort of set theoretic intersection of squares. Did you see what I mean? Go ahead.
Sorry, why doesn't Björner's result follow from Fishburn? I'm a bit confused.
It does. The history went haywire earlier. And he was aware of that. So he wanted to prove this using FKG. And Lam-Postnikov-Pylyavskyy proved their result through Schur functions and doing explicit injection to prove monomial positivity. And but that leaves a sort of a question. I should have said that. Yeah. So maybe let me write that here. So so the real theorem in that paper is Schur function monomial positivity. So S mu minus alpha times S nu minus beta. So that would be emulating the denominator here. And that would be less or equal. And then this is monomial positivity then product of two corresponding Schurs. Okay? So Lam-Postnikov-Pylyavskyy proved the Schur positivity here. That's an algebraic proof which does not generalize. But this proof does generalize, and actually, so I have 2 minutes. So let me tell you what we did without kind of telling you. So we found. So what we did is we found other polynomial analog of the LP result. We found a multivariate polynomial analog of that result. So other polynomial analogs of that result, and the multivariate analog of that result. This is for all posets. So you need to take the framework that we've been doing for the Fishburn of lower ideal and upper ideal. So here we have 2 lower order ideals. But in here, we need both 2 lower ideals and 2 upper ideals. The formulas get to be a little too long for me to write in the remaining 1 minute. But multivariate analog is a giant summation. Which is analogous for Schur function, except as you know, Schur functions require strict positivity here and non-strict that way. We cannot do that for. It's a little annoying to do that in generality of all posets. Lam-Postnikov-Pylyavskyy needed to do that, and they did. Which made the paper slightly less accessible, and we avoided that. If you do order polynomials, that's going to be a special case of just increasing, and we do it for all. And we get analog of the kind of like sort of like a variation on Schur function, kind of multivariate summation, which is still true. You still get the multivariate inequality here, and that leads us back to this example. So one can write an analog of this result in the multivariate case, but it won't give you any. There is no symmetric function positivity here at all. It's going to be just a positivity of some multivariate generating function with generalized order polynomial. Okay. And that's it. Thank you.